Hello everyone. I'm welcoming you on our webinar on 3D scanning. My name is Andrei and we're going to start in a minute. I just want to make sure that everything is plugged properly and you can see me and hear me, which you should be able to do at this point. So if you can hear me and see me, it would be nice of you if you type this in a live chat, so I will know that everything is connected properly. And we're going to start in about a minute, just in case if someone will join in the last minute. Okay, thank you very much. And we're going to start. What we're going to start with is some rundown of what we're going to talk about. So I'm going to cover some general topics that we're going to discuss. So first of all, I want to start with some general physics concepts, just to make sure that we are on the same page, because lots of these concepts will be needed for us to better understand the principles behind the scanning. So we're going to talk a little bit about signals, their types, the sources and receivers of the signals. We're also going to talk a little bit about such concepts as reflection of signal, absorption of it, and dissipation, which plays a great role in the scanning process, and how we can avoid certain problems related to them. And of course, we're going to talk extensively about the Calibry itself, the scanner that we're going to use. I'm going to talk about the cameras, the light sources that we're using, and the sensory units. We also talk about structural light technology, what kind of grid we're using to prepare the models, how this grid is used, what kind of lines is there. And I'm going to show you a couple of scanning demos and tricks to demonstrate how you can make your scanner results better, what kind of patterns and angles used to scan certain models, and how to handle certain cases of reflections and glares. And in the end, we'll have a Q&A session where you will be able to ask questions. Actually, you can ask them just right away in the comment section here. And in the end, I will answer some of them. And if there will be no time, you can always address our tech support, and we'll cover your questions later. So let's begin with some physical concepts first of all. So what we have to understand here is that the scanning, optical scanning, is just a case of sensory perception. So we have some kind of source of signal which emits the signal to the receiver. So there are three major components. So there's a source of signal, the signal itself, and some kind of sensor which can perceive the signal. I'm using the light here as the source, as the most obvious example. But we have to remember that we also can use, for example, speaker as a source of a signal, and then the signal would be obviously the sound, and the receiver would be some kind of microphone or our ears. So it really doesn't matter what kind of signal we're using. But what we see in here is so-called direct exposure case, when signal goes straight from the source to the receiver. Although this is very common, it's not really something that we're going to be interested in, and we're much more interested in so-called indirect exposure case. So what happens here is that the signal from the source, in this case light, goes to the object that we want to inspect in some case or analyze, and this object reflects part of this signal to the receiver, which we already perceive as a signal, and create a mental image of this object. So what is important to realize here, first of all, that the sun in this example is independent source, so it's not part of the sensory system itself. The sensory system is on the right here. And this object that we have can absorb certain parts of this signal. And then the signal that is being dissipated and reflected away and partially hitting our eyes or our sensor is somewhat changed. And by changes of this signal, we can make predictions and analyze what this object is. But before we go into this, I want to say a few words about the nature of color and the nature of black color, especially because, well, it's really one of the trickiest objects to scan, and I just want to emphasize why it is the case. So when we see an object of a particular light, of a particular color, what actually happens is this object absorbs all the visible spectrum except certain parts, certain wavelength that our eyes or our sensors perceive as the certain color. So for example, if there is a red car, it absorbs all other wavelength of light and only reflects a red, and when it hits our eyes, we perceive it as such. The same goes with the other colors as well, but black in this case is somewhat special. So black is actually absorbing all of the visible spectrum. And what black really is, it's not some kind of particular signal, but actually the absence of signal at all. So in case if we imagine that certain color is a music note, in this case the black is sort of like silence. And now we're going to talk about the scenarios that we can encounter when we see or scan certain things. In this case, I'm inviting you into this sort of darkened room, and what we have, the source of light and the sensors that we're using to get the data. And there are three major scenarios that can impede us from really getting any data from the object. So to see the object, what we really need is this light, this signal, being reflected from the object back to our sensory unit. In this case of reflection, we can really see or hear, in case of a sound, for example, what is going on and how far the object is. But when we send certain signal to the object, it might be, first of all, fully absorbed and nothing gets back. So we send in the signal, but we're not getting anything back. And in this case, we have no signal and we see the dark color or silence in case of sound. The sound also might be just scattered, so it can be reflected away from the object, but this reflection is not really getting into our sensory system, so this signal doesn't give us any information about this object. And finally, it might be just dissipated, so it misses the target and goes indefinitely in space and then just fades away. But what is important here also is that we here combining the source of signal and the receiver of this signal, the receiver, our sensory, in a single unit. So what we have before is the separate source of signal and the receiver. In this case, they are combined into. And it's not something, it's something that we also use in our scanning, but it's not something that we invented. It's not something that we invented as a species also. So for example, bats and dolphins using pretty much the same system for millennia. So they're using sound instead of light, but the general idea is pretty much still the same. So they emit certain kind of signal into the outside world. This sound being bounced off certain objects, or it might be their prey or parts of their environment, and then the signal gets back to the animal and they can analyze what's going on out there. And we kind of borrowed this technology and we're using it in sonars and radars just to track certain objects in the outside world. And that's pretty much what we use in scanners too. So we emit the signal and we get something back as a source, as a signal that we need to use to create a mental image. So we're going to talk a little bit about those reflections and absorption cases. So I just want to emphasize that we also sometimes use dissipation as a tool to avoid detection. So for example, that's basically at the core of stealth technology. So when we emit a signal towards an object of this radar station, for example, it hits this plane, which is Lockheed stealth plane, which dissipate the signal in the different directions. It scatters it away, and none of this signal getting back to the radar, which, as we've been discussing, is the definition of detection. And in this case, we have nothing in return. So in scanning, this happens sometimes too when we have a tricky object that just dissipate the light that we send to the object and we hope to receive back. So scattering is one case, and the other one, as I said, is absorption. And black objects might absorb all of them. And the classic example of absolutely black object which consumes all of the light is a black hole. So even if we build a scanner the size of the Death Star from Star Wars, we will not be able to scan a black hole because it's just so massive that all the light is being absorbed by it, and we cannot really get any signal back. But in reality, of course, the real objects are not ideally black, are not that massive, and they still dissipate a certain amount of light, and they still reflect it. So we can pick up those snippets of light and build a mental image of what's going on. But it also depends on the sensors that we're using. So the more sensitive the sensor system is, the more high-quality image we can use. So for example, cats can see much better in darkness than we do, and what we perceive as complete darkness, well, for them it's moderate lighting conditions. So it really depends when you're trying to find a way in the darkness or try to scan dark objects in a dark room. It really depends on what kind of equipment we're using. So let's now turn to the equipment itself. So here's our Calibry scanner, and it has 4 major components on the front panel. And I like to combine them into 2 separate groups because, well, they have sort of different tasks. First of all, first group is the main group, which is geometry camera at the very top of the scanner and projector at the very bottom. These 2 combined create actual 3D surface. So how it's done, the projector projects the light, it's the source of light in this pair, and it projects not just some ordinary light, but very special one. And by distortions of the signal, we can analyze what this object is and how far it is. And we pick up this signal, reflected signal from the projector by our geometry camera. And thus, analyzing this data, we can create this mental image of what's going on. And in the middle here, there is a texture camera and 6 LED flash rim, which is another combination of light source and the sensor. So this flash rim creates light conditions for texture camera to make pictures, and texture camera making colorful pictures. The geometry is monochromatic, so it only cares about the brightness of the color. So we do not really need a color for making 3D model, but if we need a sort of this shrink wrap of color, this texture wrapping of the model, we using this texture camera to create this colorful image of our model. It also used for non-geometrical tracking when we use marker or texture, for example, as a tracking mode, but that's a completely different story. Let's talk a little bit more about this first pair, because the geometry camera and projector are actually main players here. It's them who actually create the 3D surface. So how they do this? This is the grid that is projected by the projector. So here, the white grid projected by our Calibry scanner, and Calibry Mini uses blue light here, but the structure is pretty much the same. So there are 2 types of lines. There are sync lines, which are almost vertical. They're slightly angled, but I'm going to refer to them as vertical lines. And data lines, they are almost horizontal, but they are inclined like 15 degrees from sync lines. It's not a straight angle here. And what is important here is that sync lines, they do not create actual data. They are just auxiliary tool that scanner uses, first of all, to stitch different frames together and create this model that we're trying to make from separate frames. And data lines are actually adding those points to the point cloud that we're trying to make. So let's take a look at the typical frame that Nest receives from the scanner. So you can see the part of the light grid on the surface of a wall. And once again, I just highlighted the green lines are data lines, which are used to create data, actual points in the model. And orange lines are just sync lines, so there is no data here. And you can see in the middle, sort of zoom in part of a typical frame. And those green dots that you see here, these are actual dots from the model. And orange line is just imaginary, it's not really there. And you can see there are gaps between those green stitches, so there is no data. And you can see on the right the typical final frame, which contains those stripes. So how is it used to create actual grid patterns? How this grid pattern is used to create a model? I'm going to show you 4 types of settings which might be used for scanning, might be used as a demonstration of certain problems that you might encounter. As you can see, I'm using a tripod here, which we not generally recommend because it's the handheld scanner after all, and it generally should be used in a hand. But just to emphasize certain problems that we may experience, I want to use this tripod. So first setup will be vertical. When you can see those vertical sync lines, I'm using calibration board from the Calibry Mini, but not for calibration, but just for a demonstration here. So you can see those vertical lines being ideally vertical. The scanner itself is slightly inclined because, well, vertical position of a scanner and vertical position of lines is not the same thing. There is a little angle between them. But what is important here is that vertical synchronization lines here are straight vertical. On the second setting, on our second setup, I'm positioning those sync lines horizontally. In order to do this, I'm tilting the scanner 90 degrees counterclockwise, as you can see on this picture here. And this will be our setup number 2, and I'm going to show you in a minute what kind of results you can achieve with this and why it's not the best condition to scan. And another one is when we once again have horizontal lines, but these are data lines, not synchronization lines. So as you remember, there is a 15 degrees angle between data lines and normal to the sync lines. So what you can see here, I'm tilting the scanner 15 degrees counterclockwise to make those data lines horizontal. And the fourth case is what we actually recommend to use in most cases, is when you actually use the scanner as a handheld device and you move in scanner around sort of from vertical to horizontal position like this, and we gonna look what kind of patterns these 4 methods create. So in order to do this, I'm switching to the Calibry nest when I just want to show you how these patterns actually look when scanning. So this is our first case when we have synchronization lines being vertical. And you can see right away that there is something wrong about this model. So you can see those stripes here, stripes of data, and they are especially visible over here. And you can see those diagonal lines. These are exactly data lines that I've been talking about. So scanner basically gathering data only from those lines, and the space in between those lines is sort of empty. I mean, there is still a certain amount of data which Nest can use to create part of the model, but still there are lots of gaps that Nest has to void. Nest is our software that we use to process the models. So that's definitely not the way to go. But when we position sync lines horizontally, this is our second setup, the case is actually might be even worse than that. So you can see that we have those huge gaps between data lines. Those data lines, once again, they are inclined. Here they are. The orientation of them is slightly different here. I'm going to increase their size a little bit so they will be more visible. So you can see those data lines, and here in this area it is more or less possible to create decent surface out of this data, but as you can see in between them there is really nothing there. And when we are trying to finalize the model like this, what we're going to see is that those stripes of data will be more or less fine, but the data between them will be extrapolated. So it's not real data, it's just a mathematical calculation of what this surface might look in between. So definitely not the way to go too. So if you're holding your scanner statically, that's one of the problems that you may encounter. So just always remember to move it around. And now for our third case, when we have data lines horizontal. And this is even worse than the previous, because you can see that we have those huge gaps in the model, and all data lines are positioned in those lines over here. And this is really one of the worst cases when you incline the scanner like 15 degrees to the counterclockwise and move it parallel to the data line. So all those data lines are just gathering data in those long stripes, and there will be those gaps in between them. So it will be really difficult to create a good data out of this. So why rotational pattern is different? When you change in the rotational pattern, it creates those snowflake surface, which creates much better coverage of surface. And in this case, it's much easier to create a decent surface. I just want to emphasize this point, and I'm going to open the frames here. And if I pick up random frame here, you can see those data lines that we've been talking about, those stripes of data, and vertical sync lines should be in between them, and you can see that there is no data. So that's just a typical frame. And when I just pick up random frames here and select just like 5 or 7 of them, you can see that those frames being shot in a different angles, and they create this sort of snowflake structure, this crossing structure, which gives you just a better coverage. And this is much easier to calculate what's going on in between those models. So when you have enough of this data, you can have a much clearer data. So this is definitely the way to go. So if we look at the final result of this, first of all, here is this pattern that we've been talking about. So the static or linear pattern, when we have basically all data concentrated along the same lines, and we have huge gaps between them. And on the right here is what is called dynamic or rotational pattern. And you can see that the data scattering is much higher there, and it's easier to calculate what's in between. So the result of finalization, not surprisingly, will be much better on the right side. So you can see those very specific lines on the left side. These are the lines where NEST has to calculate what's in between those gaps. It tries its best, and sometimes it gives more or less decent result, but in this sort of exaggerated cases, it creates those lining patterns. And you can see on the right side that the object is much clearly scanned. So this is one of the greatest examples of how you should really use the scanner to get better results when you prepare your models. But this is all that we've been talking about so far, is when nothing stands in the way, when nothing prevents us from getting a good model. But what is important is to understand how to deal with the external conditions. So in order to understand this, I'm going to show you how the scanner actually sees the world through its lenses. And I'm making a little setup here with some random objects here and a light source so that we can see better what is going on. And we're going to start from the texture camera, which, because it's just the simplest camera to understand what's going on, it's basically just a sequence of frames which I combined into a little video sequence of about 600 frames. It's not all of the frames, it's just every second frame, because every odd frame would be the frame from the geometry camera. So as you can see, it's just, it might look a little jumpy, but the thing is that it's basically the colorful video which we use, frames of which we use to create this colored surface and atlas for the texturizing the model. But once again, this is sort of auxiliary tool when we use in marker mode, for example, or texture tracking mode, or when we want to texturize the model, we need the data from this camera. But what is much more important here is how geometry camera sees this. And even before I start the sequence, you can kind of see that this is much darker. Those frames are much darker, and it's done for a purpose. And as you can see, there is no color, it's only just brightness. And I intentionally closed the grid here, so we cannot see the grid for now. And you can see how dark those frames are. It's done specifically for the very simple reason, so that this grid that we project on those objects will be much more visible on those frames. And I'm going to show you how it actually looks with the grid on. So you can see it right away on the first image of this sequence. But what I want to emphasize right away is that, as you can see on wider objects, it's clearer, so it's much easier to see the grid on, let's say, those sides of the books, for example. It's very clearly seen. And on some darker objects, so for example, there is a phone and the lamp itself, as you can see, it's difficult to see, but for a scanner, it still might be enough to get a good image. And what is important here to emphasize also is that we have this glossy surface of the book, and you can see the reflection of the lamp here. I'm going to start the sequence and pause at a certain moment just to emphasize this point. So you can see that the grid is harder to see on glossy surface right away, but when we also have a source of light here, it's almost impossible to see in this area. So when you're scanning something and when you're using external light, when there's a light bright conditions, it's much harder for the scanner to get the data from the grid, because it's basically the light source, the outside light source, the ambient light, might be brighter than the brightness of the grid, and it will be difficult to scanner for detect. Especially for the darker objects, as you can see here. So for example, on a frame of a painting, it's much harder to see, but it still might be enough for the scanner to get the data from there if nothing impedes. So that's why we generally recommend to dim the light when we're scanning something. And I just want to emphasize this point by giving you this example of ambient light influence. So you can see on the left side here is a darkened room when I'm once again using our scanner on a tripod, and I'm aiming at the wall, and you can see this circle of the grid very clearly, very distinct, and there is in the middle up the part of this grid. So it's very contrast, it's very easy to see, and on the left side, when I switch the light on, you can see that it's much more difficult to see the grid itself, and it's not that contrast on the on this sample over here at the bottom. It's still visible enough to create a surface, but it might be more difficult if the light is even brighter. And it's also true when we're scanning, let's say, objects which have a curvature, which happens quite often. So what you can see here, I'm using Calibry Mini over there, as you can see, with a blue grid light, but the general idea, once again, it's pretty much the same. If we have a source of light on the left here, on the right, sorry, you can see that it's very difficult to detect the grid in those areas, those overlighted areas, overexposed areas. And it's also important to move your scanner around to move this part of the grid which is clearly visible for a scanner. And if you move around this object and let the scanner to collect and pick this data from the areas where it sees clearly, you will get much better result. Sometimes when you still have to scan in the areas where you cannot control lighting conditions, for example, or the object is just absorbing too much light, you can use our projector brightness option to make the grid a little bit brighter, so 50% in this case. So you can see on the left is base brightness, which is basically enough for most of the objects here. But if some objects just absorbing too much light, if we're talking about dark objects, or if the conditions, lighting conditions, are unfavorable and you have problems, the scanner has problems detecting the grid, you can always go to this black droplet, which increases the brightness of the grid 50%. But even this might not help in case of glossy surfaces, for example. And it is important to understand why is it so. So when you're scanning a glossy surface, the light is basically being reflected away, like in those cases of stealth technology plane. So we're sending the light to the surface and it's just being scattered away. On the matte surfaces, which I depicted here on the right, you can see that we have those nooks and crevices on the surface which disperse the light, which makes it statistically more likely that the parts of this light will be reflected back to the scanner. And in case of, in left case, when surface is too smooth and too shiny, the light just being reflected away with the same angle it falls on the surface. So how can we deal with this? Well, we can use pretty much the same principle of reflection here. We know that we need a certain angle to reflect this light back to the scanner. And as you can see, if you use a bigger angle to scan glossy surfaces, the light just being reflected away, and scanner doesn't really see, the geometry camera doesn't really see the data from the projector, from this grid. And by changing this angle, you can just pick the angle when you scan a shiny surface, which helps you to reflect this grid back to the geometry camera. So it will be much easier to do. And I'm going to show you an example of this through Live 3D. It is actually how it's seen in the scanner. So I'm just put the phone on the floor and there are markers around it. So you can see that we can clearly see the floor around it, we're getting data from it, but there is nothing in the middle. This rectangle is basically empty because the light from the grid from this angle just being reflected away. But if I change the angle of scanning slightly, you can see how this rectangle will fill with data little by little. So by adjusting the angle of scanning, you can find this magic angle that just reflects back this grid from the object, and that's one of the tricks that you can use to scan glossy surfaces. And I just want to show you how it really looks from the perspective of the scanner. And to demonstrate this, I'm going to make this little setup here where I'm putting different samples here. So there will be a black surface, a white surface, and I use this glove as a representation of gray, so something in between. I'm using markers here because there's not much geometry here. And you can see from the very first frame that the white paper is clearly visible here because, well, it reflects light very good, and the geometry camera has no problems picking this light up. You can sort of see the pattern, this linear pattern on the glove, but black surface is pretty much invisible. And once again, it's just from this angle. If we change the angle from which we're scanning, I'm going to pause here in a key moment, you can see that in this angle, the grid is visible almost as good on black surface as on a gray surface. White surface is of course a winner here because, well, it just reflects light perfectly. That's basically why it's white. But we do not really need this high quality of grid to get the surface. This what we see on the black surface and on the gray surface is basically enough. So by changing the angle, we can really find the spot to scan trickier objects, no matter if they are black or if they are shiny. And you can also see the markers here are clearly visible because they have this metal part in them, which is white and which is reflecting very nicely. And you can see if there is a cross that is on the marker, that it's the condition for detection of this marker. But once again, that's a slightly different story. So just to emphasize the points that we just made, I want to make a few points here. So what you need to remember when you're scanning objects here is you have to move your scanner around and tilt it from side to side to change the orientation of the grid that is being reflected from the object to the geometry camera, and thus creating the 3D structure. And it helps you to make this snowflake structure better coverage of the surface with data, which is much easier for NEST to calculate later on. Once again, try to avoid massive light exposure, and if you have this opportunity, try to dim the light in a room, or try to find a shadowy area where you can scan more comfortably. It will give you better results because the grid will be more contrast. When you scanning glossy objects or curvy objects, just try to avoid glares on the objects if at all possible, and try to move scanner around once again to have this good spot on a different places so that the scanner pick it up and create a better model for you. And when you're trying to find, when you're trying to scan glossy surfaces, just try to find this magic angle that would hopefully help you to get the data from a shiny surface as well. So these are basically the tricks that you can use to make your scanner results better. So thank you for your attention, and if you have any questions, for now you can ask them in our chat here, or you can always address us at our support email at support@thor3dscanner.com or support@calibry3d.com. So thank you. You can ask your question now. And we're going to spend a few minutes answering those questions, and then you can just ask your additional questions on the email if you like. How this device can be used for scanning plastic transparent components. Well, with plastic transparent components, you should remember that this grid, first of all, it depends on the level of transparency of the object. So some murky objects will still give you enough reflection back to get part of the surface. If it's really transparent, like ideally transparent, it might be really tricky to scan because light just going through this and getting scattered, and the angles of the light will be very difficult to predict. So in this case, it's one of those cases when it's really might be a good idea to use mattifying spray just to increase the reflection of the light. So the detection of light will be easier for the scanner. Would it be possible to buy markers for Calibry scanners? Well, you don't really need to actually buy them. You can print them by yourself, and we're using sticker paper, just ordinary sticker paper, which we can print those markers on and then apply to the object. You can download the file with the markers from our website and just easily print it out. If you address us in our support email, I can even send you the tutorial how we actually do this. I've been doing this for a while, and I can easily give you pictures of how it looks, what kind of paper to use, and how to print it better to get a better result, and how to cut it. By the way, there are a couple of nice tricks that you can use to cut them much more easier, so you don't have to use scissors for this. But the only thing that you have to remember when you're printing your markers yourself, try to avoid glossy paper. Sometimes those stickers, they're using this really glossy paper, and it reflects light not in favorable way, and it's much harder for the scanner to detect those. So you have to use matte paper. It's usually very specifically stated on the package. So just let us know on these emails that I'm showing you here, and I'll show you how to do this. Okay. What do you recommend adding to transparent or black plastic parts to assist the scanning when markers may not be enough? Well, markers themselves will be enough for, the markers themselves will be detected. It's the problem of the detecting the surface here. And really mattifying spray might help in this case because it just helps a scanner to see the actual surface, and the light from the grid is not being scattered or not just going through the model. Is it possible to use square markers? Well, the markers themselves should be of circular shape, but you don't have to make the shape of a sticker round. So you can use just a rectangular part on which there is a round marker, which we do all the time, and it works nicely. What is the smallest item that can be scanned with the device? Well, it depends, first of all, on the scanner that you're using. There are two of them. There is a Calibry and Calibry Mini. Calibry is used for objects, well, generally we recommend to use it for objects from 30 centimeters up to several meters. And for Calibry Mini, it's below 30 centimeters. So if you need a smaller object with higher details, Calibry Minis, of course, have different optics and it has higher resolution. So the quality image of a small components will be much better in case of Calibry Mini. Why does the Calibry Mini has blue light as opposed to white light in the regular Calibry? It does want to work better for black or reflective surface. Well, the reason why we use blue color for Mini is because it was not in the last, not at least made for scanning parts of the body for prosthetics reasons. So, for example, the ears or a nose or the facial features or something. And blue color just has better reflectance from the skin. It's much easier to detect on the skin because, for example, if we using a red color, for example, it's much more absorbing by the skin, and blue color is sort of more cold and it's getting reflected back better, so it's much easier to detect. Okay, well, if there is no more questions, thank you very much for your attention. And once again, you can send your questions to our emails. So thank you very much for coming to our stream, and I'll see you next time. Goodbye.